Good afternoon, everyone. My name is Ting Wang from East China Normal University. I'm honored to have this opportunity to give a presentation. The topic that I want to share is machine learning empowered intelligent data center networking. Data center is known as the core infrastructure of cloud computing. However, with the rapid rise of data center scale, the network optimization, resource management, operation and maintenance, and the network security have become more and more complicated and challenging. What's more, the burgeoning development of 5G has spawned numerous complex real-time, diversified, and heterogeneous service scenarios. It is universally acknowledged that data-driven machine learning technologies have made tremendous progress in recent years. Quality of academic research has primarily demonstrated that machine learning could make more effective decisions and optimizations in the ever-changing network environment. The combination of machine learning and data center can benefit each other. From one point of view, data center is a perfect place to serve as an efficient AI platform, which can provide substantial resources and efficient network communication for the distributed machine learning cluster. From another perspective, the AI technology will also greatly help the data center network to improve the network service quality and the operation maintenance efficiency, so as to cope with the new challenges brought by the increasingly complex network management and dynamic flexible services. Although the research on intelligent data center networking has made great progress, it is still confronted with many challenges. To be specific, the high networking complexity, highly dynamic environment, diverse traffic patterns, and diversified services all may make it not so easy to directly employ machine learning technologies to data center. Here we summarize four key challenges encountered in current research, including data processing, collaborative optimization, machine learning model selection, and standardization. Now let's explore more about the machine learning empowered intelligent data center networking. Here we classify the application scenarios of artificial intelligence in DCN into 9 different fields, namely flow prediction, flow classification, load balancing, resource management, energy management, routing optimization, congestion control, fault management, and network security. Now let's discuss this one by one. Flow prediction can help grasp the characteristics and trends of network traffic in advance, providing necessary support for network optimization and decision making, and serving as a priori knowledge in many fields, including routing optimization, resource allocation, and congestion control. However, the huge scale of network and the diversity of services impose great challenges in dealing with the traffic with irregular and random distribution in both time and space dimensions. Here are some of our insights for flow prediction. Firstly, we should pay attention to quality of data sources. The performance of flow prediction heavily depends on the quality of source data with respect to authenticity, validity, diversity, and instantaneity. Besides, prior knowledge also matters. The performance of machine learning algorithms in exceptionally complex spatial temporal scenarios is still limited, but partially because they require additional expert knowledge support, where the model learns through the features pre-designed by the experts. Moreover, the solution should have the ability of anti-interference. For example, The network upgrading, transformation, and the failures typically can cause sudden traffic fluctuation, and this abnormal data will interfere with the ultimate accuracy of the model. Similar to flow prediction, flow classification is also widely used as the priority for many other optimization modules. However, the highly dynamic and differentiated traffic and complex traffic transformation mechanism greatly increases the difficulty of traffic classification. Here we list the several key concerns that need to be addressed. Number one, fine granularity. A fine-grained and accurate classification scheme can help allocate network resources efficiently, ensuring a better user experience. However, most of the classification schemes are only based on a rough generation classification skill, for example, singly based on the network protocol. Besides, the computing overhead, monitoring overhead, stability, and feasibility also need to be considered. Number two, flexibility and robustness. To meet various service needs, flow classification should consider timeliness and effectiveness of classification, which could help services meet their SLAs. When encountering network anomalies such as data, packet loss, and retransmission, the efficiency of robust flow classification solution should not degrade. The load balancing problem is usually formulated as a multi-commodity flow problem, which has been proved to be NP-hard. The traffic in data centers usually changes in milliseconds or even microseconds. However, traditional solutions lack the flexibility of dynamic adjustment according to the real-time network environment status, which may lead to imbalanced load distribution or even network congestion. Here, machine learning can help the network self-learning realize the self-decision of flow scheduling strategy and self-adaptation to the network environment. Here we list two key challenges and concerns. Number one, capability of network stacks. Different protocols may coexist on the same data center network, which may result in unequal distribution of network bandwidth among different network users. Therefore, the solutions may pay attention to the capability between different network protocols and prevent unfair resource allocation caused by the different protocol parameters. Number two, dynamic of network flow. In respect of the dynamic of network traffic, it is necessary and beneficial to adjust the threshold and the priority of flows in time, especially for the mixed flow scheduling problem. Resource management directly affects the overall resource utilization efficiency and the resource availability, and further affects the user experience and the revenue of service providers. However, with the increasing complexity of network infrastructure, the explosive growth of the number of hardware devices, and the growing demand for services, the traditional solutions can no longer effectively deal with these problems. Machine learning can make up for the deficiency of traditional methods by learning historical data to dynamically make appropriate management strategies adaptively. Here we summarize several key concerns which deserve to be further studied and addressed. The first one is adaptability to multi-objective and multitask. One qualified intelligence solution should fully consider richness of scenarios and requirements and should be able to adapt to multi-scenario and multitask network environment. Besides, the data center is usually a virtualized environment. The flexibility of virtualized resources can make vulnerability or fault propagation faster and fault recovery and fault resource tracing more difficult. From the perspective of resource life cycle, the allocation, utilization, and recycling of resources occur frequently. Currently, intelligence solutions focus more on the prediction of resource location and the maximization of benefits in the process of resource location, but lack related studies on resource collection and recycling. In data center networks, routing optimization is one of the most important resource areas. However, according to our investigations, there are very limited number of papers studying machine learning-based routing optimization in data centers. Based on the limited research work in this area, we summarize several potential research opportunities. Number one, multi-objective optimization. Considering the diversity of traffics with different priorities, how to provide differentiated routing optimization policies is deemed as a challenging task. What's more, the decision-making of routing policies may also depend on the preliminary results of some other optimization models, such as traffic identification and classification schemes, where it will involve collaborative optimization of multiple learning models for multiple tasks, which further increases the difficulty of optimization. How to balance the optimality of solutions and computational complexity of algorithm becomes a key issue. Number two, the model selection. Choosing an uh, appropriate and effective machine learning model is the first and the most important step towards intelligent routing optimization. However, in most cases, the existing machine learning models cannot be applied directly to the network routing optimization. Recently, some machine learning-based congestion control algorithms have been proposed. From the perspective of the decision-making mode of congestion control policies, we divide the existing machine learning-based solutions into centralized and distributed congestion control. The centralized scheme detects, avoids, and mitigates network congestion through unified scheduling and centralized management of decentralized network sources. Compared with centralized schemes, distributed schemes decentralize the decision-making authorities and focus more on end-to-end congestion control, concentrating on the collaborative algorithm design on distributed network devices and hosts. Here we summarize several key problems that may hinder the improvement and the implementation of congestion control schemes, including latency, scalability of machine learning algorithms, scheme evaluation, and microburst tolerance. The current data center network OM model is still passive and already depends on manual operations, which is inefficient and not intelligent. Different stages of the fault management lifecycle include fault prediction, fault monitoring, fault location, and fault self-healing. How to effectively extract the critical information with fast sensing capability has been the primary concern of current research. The large-scale nature of data center network and the high richness of the network data make fault detection extremely challenging in DCs. Likewise, fault detection, accurate fault localization is also a very complex and difficult problem, which has been proved to be an MPC problem. How to achieve rapid self-recovery after the occurrence of a failure and ensure that the service is not affected is the last but very important step of network OM lifecycle. Likewise, we also summarize some critical points of machine learning in fault management, including false negative samples, date imbalance distribution, node disturbance, complex dynamic environments, and so on. Up to now, machine learning has been gradually introduced and applied to various fields of data center network and has made certain achievements. However, the current research is still in its infancy and need to be further improved in various areas. From the perspective of machine learning model selection, according to our investigation, deep learning has gained the favor of researchers because of its good comprehensive ability, accounting for over 50% of all solutions. Supervised learning and deep reinforcement learning are ranked second and third, respectively. From another perspective, currently, as we can see from this figure, the researchers mainly focus on flow prediction, resource management, flow classification, flow scheduling, and load balancing, but pay less attention to fault management, routing optimization, and network security and congestion control. Overall speaking, the research on applying machine learning to data center networks is still at an early stage. There are always many opportunities to further explore the potential value of applying AI technologies in various fields of data center networks. It is clear that the network intelligence will inevitably become the future trend of data center network development, driving the data center network from SDN-enabled automatic network to AI-driven intelligent network. That's all. Thank you.